Thank you to the organizer for this conference. For me, it's the first one since almost 3 years, so it's a rebirth. Also, maybe say a little word to Pierre-Yves Coursol, si tu m'entends, n'oublie pas, envoie-moi un message. And okay, so my talk is actually about vortices. Okay, so Uli talked about vortices this morning a bit. He talked about higher dimensional automaton a bit, and also about realization. And this is about what can happen in bad situation with realization. Okay. So the first thing is, what is a local order? So basically, it comes from the idea that a partial order is a kind of infinitesimal thing, like Rn is for manifolds, right? It's the same idea. So a pose space is just a topological space, a partial order, and one requires that the graph of the partial order is closed in the product topology. It is a coherence axiom. Well, actually, in the first place, it comes from functional analysis. So explaining the reason for this requirement is not completely obvious. But otherwise, you could choose topology and order completely independently, which is not a good thing. And so you have a notion of morphism, which is very natural, required that the morphism preserve topology and order. It forms a category. And what one can remark is that the underlying space of a pose space is always Hausdorff because of the closedness property. Okay, so a local order is just a collection of pose space. And what you require is that each time you have a point which belongs to two pose spaces, then you can find a small open neighborhood of P on which both order on V and U agree. Okay, you cannot require that they match on the whole intersection, but you are sure that you can find a neighborhood which is sufficiently small so that both coincide on this. And this is a big difference with usual manifolds, but it's very important, actually. Yep.
Why can't you require that in intersection? Is that an obvious reason?
Why you cannot require this on the whole intersection? Alors, if I had a blackboard, it would be much easier. So imagine that this is an half circle and this is an half circle. If you put them like that, you have a whole circle. Okay. So imagine you turn that way. So here, this point is less than this one. But here, this point is less than this one. And so in the intersection, you would have this one less than this one, and this one less than this one. Okay? So you cannot expect to have a perfect match on every intersection. Okay? So you also have a notion of morphism, but which is a bit more involved than the one of mere pose spaces. So each time you have a point P and its image F of P, and each time you take a pose space containing the image of P, you should be able to find a small neighborhood of the image of P, and on the other side, a pose space containing P and a neighborhood of P, so that F induces a pose space morphism from the neighborhood of P AP to the neighborhood of FP, which is denoted B here. Okay? And you cannot actually make something simpler. Otherwise, the category have poor properties. Okay, so now the question is, where do these objects come from? Okay. For my part, I discovered them in the paper by Lisbeth, Eric, and Martin in 1998. But actually, it appears in the book of Seagal about mathematical cosmology and astronomy. So it's about general relativity. So this book appeared at the same time of the book by Hawking and Ellis, large-scale structure of general relativity. And the main difference is that in that book, the author really take into account the possibility of a space-time with time-like loops. And therefore, it naturally comes to the definition of local orders. So of course, as Ulrich talked about this morning, the notion was also introduced once again in the paper by Fajstrup, Hubo, and Hausen, but in order to represent concurrency. Okay. And in between, there were a paper by Jimmy Lawson, which deal with local order and conal fields on manifolds. And actually, all the weird and pathologies one can find on local orders are all out of the scope of this paper. The paper by Lawson actually establishes that the intuitive local postspace, in some sense, comes from something which is called conal fields. And the conal fields are the light cones in general relativity. Or actually, there's an abstraction of it. Okay. So what do they have to do with concurrency? So I would like just to briefly recall the construction of the realization of a precubical set. But instead of considering the usual presentation that was given to you this morning, I prefer this one because it is more straightforward in some sense. So as before, you define the precubical set as presheaves over a small category. And this small category is one. So the objects are the natural numbers. And the morphisms from A to B are the words of length B with A occurrences of X. So once again, it would have been much easier with a blackboard. But you can imagine this as the inclusion of a square of a cube of dimension A into a face of dimension B. And the composite is just given by replacing the occurrences of X in beta by the letters of alpha, as on the picture. It really matches the composition of function. So as before, a precubical set is just a functor from the opposite of the category to set. The precubical set morphism are just natural transformations. So I'm sorry, maybe if you are not familiar with this. It's the most natural notion you can imagine. And so if you make the hypothesis that there is no element of dimension n for n greater than 2, you just have a graph. Okay, so a precubical set from a computer science point of view should really be called a higher dimensional graph, because it is really what it is. And then we call a bouquet a graph with a single vertex. So it wears this name. You have a single vertex, and the arrows are like this. And then an automaton is just a graph morphism from a graph to a bouquet. And so it really labels each arrow with one arrow of the bouquet. And if you start from this definition, it is much, much easier to go to the notion of higher dimensional automata. So you will call a higher dimensional bouquet as a precubical set where the n-dimensional elements are words of length n. Okay. And in that case, an HDA, so an higher dimensional automaton, is just a precubical set morphism from some precubical set to a bouquet. So it's really the most natural generalization of an automaton you can imagine. So you have an example of what the bouquet is. Here you have the image of the bouquet B for the word 0xx1x applied on the word ABCDE. It just means that you remove all the letters which correspond to letter 0 or 1. Okay. Well, and so now there is something to say about the bouquet, is that those precubical sets are not geometric. Okay. So in the original paper by Lisbeth and his co-authors, the realization of precubical sets as local orders was only possible for geometric precubical sets. Okay, or at least the proof that was given just worked for geometric precubical sets. And a bouquet is not such a precubical set. And therefore, if you want to realize a higher dimensional automaton as a local order, then you have to realize a morphism of precubical set whose target is not a priori representable. Actually, it is, but it's more complicated to prove. Okay. And so if you have a precubical set K and an element X of your precubical set K and a word W, then you can define a face inclusion from the cube which is labeled by KWX to the cube which is labeled by X. Okay. Here you just apply the word W and you replace the occurrences of X by the components of the tuple T. And therefore, you have a diagram in a certain category. Okay, so the cubes are just sets in both sides, but of course, those cubes can be equipped with many, many different mathematical structures, topology, order, and so on. And the question is, which category will you consider? And depending on the category you will consider, this diagram may or may not have a colimit. And the colimit can be bad. And this is why we are interested in colimits of local orders. So, which category to choose? Most of the time, people choose the category of displaces. And the reason for that is that this category is topological, which means that you start from the underlying sets, you compute some kind of identification, as Uri shows this morning, and there is a canonical topology on it and a canonical set of directed passes on it. Okay. So the realization is very, very easy to define and very easy to describe. But it does not mean that you perfectly understand what happens in this realization. And in particular, it could contain vortex. It's not excluded. It is possible. Okay. And so this is a vortex. Okay, so my claim is that you cannot create vortex by realizing a precubical set. But it's not obvious at all. And if you consider cubical sets, in other words, if you allow degeneracies, you can create vortices. But what one should understand here is that vortices, from a computational point of view, are bad. Okay, because imagine that this diagram is the model of two processes running together, one which is turning, okay, and the other one which is just going in line. And so it goes from this point to the center of the diagram, or the other way around if you prefer. So if you have a vortex in the model of your program, it means that when the process which goes to the origin approaches the origin, the other process is allowed to turn more and more fastly. So as the first process approaches the origin, the second one turns faster and faster at infinity, if you wish. And this should be forbidden in any reasonable programming model. Okay, if you imagine that the process which turns just add 1 to a certain variable, after infinitely many turns, you cannot say what will be the value. But there is something which is even worse than that. It is that even if you have such an execution trace, it is homotopically equivalent to a mere line. Okay, so you should imagine that this diagram is a kind of spring, and you pull on the spring stronger and stronger. And at some point, what you obtain is just one line. And this is a directed homotopy. And what it means is that if the process which goes like that reaches the origin, all the effects of the process that turns has been cancelled. Because one of the founding principles of the topological interpretation of concurrency is that two directed paths which are homotopic or dihomotopic should have the same effect on the system. And here you have one path with just one process and one path with one process that goes like this, while the other one is turning faster and faster. And these two should be the same. It's definitely absurd. So if you want to go back also to general relativity and model of space-time, even the most permissive authors forbid the vortices, because it's something which is really, it's too absurd, or at least it's very hard to see what it could mean. So there is another pathology which may arise even if you have a local order. Okay, so suppose that, I'm sorry. So of course, once you have a local order, or once you have a D-space, you could try to define a local order. Okay. And the way to do that is quite simple. You suppose that you have a D-space, so you have a chosen family of directed paths. You choose an open set, call it U, and you say that P is less than Q in U if you have a directed path from P to Q in U. Okay. But of course, the problem is that can you find an open covering of X such that those postspaces form a local order? In general, it's wrong. For example, if you have a vertex, if you have a vortex, it's not possible. But there can be even more strange situation when you reduce the open set U, the path that goes from P to Q is no longer in the smaller in the smaller neighborhood. Okay, and you can be in the situation where you have no paths which belong to all the open subsets, and then you cannot have a local order. And there is also something which is in some sense even worse. So suppose that you have indeed a local order. So you have a partial order on U, a partial order on V, and you have a witness W on which both U and V coincide. But the trick is that the paths which witness that P is less than Q and the one that P is less than Q in V are not the same. And in that case, the path relation on W does not match the path relation on U and V. And this is the problem that occurs when you have a defect of order convexity. Once again, if you go back to general relativity and to Riemannian geometrics, there is a result which tells you that around each point, there is a neighborhood which is sufficiently small to contain any geodesic in that neighborhood. And this is what we would like to have. So here we come to the Lawson correspondence, which indeed make the link between the nice local orders and something which is called the cone fields, and which comes from differential geometry, actually. Okay, so a very small reminder. So what we call a wedge in a real vector space is just a subset which is stable under addition and multiplication by a positive scalar. And you say that your wedge is a cone when the intersection of this wedge with the opposite is 0. Another way to say that is that your wedge should not contain a full line. And of course, you should think about cone as Lie cones. And if you are in the context of concurrency theory, it's the kind of state you can reach for a given state at infinitesimal scale. So a cone field then is just a map which associates to each point of a manifold a cone on the tangent space at P. So once again, if you are in general relativity, it is the Lie cone. Okay, and therefore you have conal manifolds, which are just manifold with a cone field, and the conal curves, which are the smooth curve on your manifold, such that the vector speed at every point is contained in the cone field. So you should really think about this as the Lie cones, as the Lie curves, time-Lie curves. Okay. And so the Lawson correspondence establishes a link between the locally convex local orders and the upper semi-continuous cone field. Okay. So if you are given a conal manifold, then you will say that the directed passes will be the conal curves, and the manifold with the conal curves will give you a D-space. So it's very easy to obtain a D-space from a conal manifold. Just considering the time-like curves. And the other way around, if you have a conal field which is upper semi-continuous, so upper semi-continuous means that if you have the cone field at a given point, and if you consider an open cone which surrounds this cone, and you consider a cone which is a bit aside, then it should still be in the open cone. Okay, so giving a precise definition would require a precise definition of a manifold. But it just means that if you think of the cone field as the light cone of a lighthouse, it just means that your light cone cannot just go from here to here by just a small displacement. So it's an intricate way to say that there is no vortex, actually. And the property is that if C is upper semi-continuous, then you can indeed find an open covering of your manifold such that the elements of the open covering form a local order. And each element of this local order is locally convex. So you have dropped all the pathologies that we saw before. Well, the most easy example is the circle with the usual vector field, and it gives you this space that you. But then you can also go the other way around. So if you start with a local order whose elements are locally convex, then you can recover the conal field. It's a bit more difficult. For each point P, you consider the least wedge containing all the vector speed of the directed paths that go through that point. Okay. You have a local order, so you have a notion of directed path. You consider the smooth directed paths that go through a point, so you have vector speeds at that point. You consider the wedge generated by this, and what you can prove is that this wedge is actually a cone, but you have to prove it. And the map you obtain is indeed upper semi-continuous. Okay. And so the Lawson correspondence indeed establishes, it's not a bijection, because for a given conal field, you may have many different open covering, which gives you equivalent local orders. I did not explain what is an equivalent local order, but well, if you have an idea of manifolds, you can imagine. Basically, it means that the union of the two local orders is still a local order. Okay, so the question is how colimits of local orders behave. Because, of course, you see that the local order does not allow vortices. And so it could be that the realization of a precubical set, which is given by a colimit, indeed exists, but it's something which does not match what you have in mind. There is nothing that guarantees this. You do not have the problem with these spaces because it's the topological category. So you are guaranteed that the topology is preserved. But here it's no longer the case. So my case study is actually the following one. You consider some local order U, anyone, but you can imagine the real line. You consider the product by the directed circle. And what you would like to do is to pinch the basis of this cone and check what happens. So if you pinch your cylinder at every scale, you just have one line. But maybe you could decide to pinch only half of the cylinder, or maybe less, or maybe more. So the coequalizer exists actually if and only if among all the identification you have a greatest element. Okay, so in some sense here you have a chain of of maps. If there is a maximum element on the right side of this chain, it is the coequalizer. So what happens is that when you pinch the basis of the cylinder, because of the antisymmetry, maybe you will have also to pinch other points above it. And it's possible. Well,
usually it's for 2 hours. You mean the colimit?
Yeah, well, okay. here I describe you can imagine that trying to identify all the points of the basis of a cylinder is a special kind of colimit. Is the coequalizer of the map which includes the circle in the basis and the maps which include one point, which include one point, the circle into just one point of the basis. Okay. And what we will see in the sequel is that depending on the topology of U and the choice of the local order U, the coequalizer may exist, may not exist, or may not respect the topology. Actually, everything is possible. Okay, so it is the abstract definition of what I've just described. So the map E just want to send every element of the circle to the basis of the cylinder, and the map C send every element of the circle to just one point. And you want to make these two maps coequalized. And the result is that the coequalizer of these both maps exists if and only if the family of closed open subsets containing the star has a least element. Okay. So in general, the connected component of the star is contained in the intersection of all these Klopen sets. And there is an equality if and only if U is locally connected. And in particular, if your space is connected, then there is just one Klopen set, which is the whole space. And in that case, by just pinching the basis of the cylinder, you will have to identify all the points of it. And in that case, the colimit exists, but it destroyed the topology. Okay, so, well, this slide is the exhaustive description of the local order of the colimit when it exists. It's not so interesting. It just says that above the limit where you do not identify, you still have a cylinder, and below it, you have just one line. And at some point, you need some trick to make the link between the cylinder above and the line which is below. Okay. And then the map, which identifies all the points of the set O, is actually the coequalizer of the map E and C. So if the star has the smallest Klopen subsets containing it, by identifying all the points of this Klopen set, you obtain the coequalizer. So for example, if U is R, you have the coequalizer, but the topology is destroyed. If U is the rational number, then you have no smallest element, which means that you can identify as close as the basis as you want. And then you have no coequalizer because there is no maximum element. And of course, you can also create pathological topologies, for example, by starting from the real line, which is usual topology, and consider the least topology where the star itself alone is also open. And then it allows you once again to identify as close as you want of the basis without identifying above. Okay. So here I have, in some sense, played with the topology. I've cheated with the topology. And on the next example, I would like to show that you can have the same kind of topology without cheating on the topology. Okay. So what you do is actually quite simple. You have your cylinder with the standard topology. And you have some zebras, which means that on the half of the cylinder, you turn that way. Then you consider a small bound beyond it, whether you do not turn at all, then a smaller band when you turn again, and so on. You alternate bands where you can turn and bands where you cannot move, you cannot turn. And once again, what you obtain is a Collimate diagram, which has where you have no coequalizers. It's in some sense it's the same kind of element of counterexample as before, except that instead of playing with the topology, you played with the local order actually. Okay. So we have seen that we may have pathologies. Coequalizer may not exist. The topology may be destroyed. The question is, what about precubical sets? So in the very last slides, I would like just to show you that for the two truncature of the terminal precubical set, which means that you have one element of dimension 0, one element of dimension 1, and one element of dimension 2, then the coequalizer, the colimit indeed exists as a local order, and it is not pathological. So here is a representation of that precubical set. So you have just one element of dimension 2. Here, the element of dimension 1 is actually duplicated 4 times. And the vertex is duplicated also 4 times. Okay. But the edges are not identified in a clumsy way, in some sense. But you should imagine that the 4 white dots are identified. These ones are identified also. Okay. So these points that are moving are identified. So it means that you still have a line. You still have the 4 edges of the square are identified with a circle in an isometric way. Okay. So in order to describe the local order of the realization, you have to describe the partial order around each point. So if you consider a point in the middle of the square, it's easy, it's just a square. If you consider a point which is on the edge, as I show you, what you obtain as a neighborhood is the gluing of the 4 rectangles here, which are glued as this kind of a fan. And the order is depicted by the arrows. So in some sense, it's a sub-postspace of R3. So it's something that you can easily understand. So here you have an example of what happens. You have the white dots, which moves. Here it is identified with the 3 other edges, 3 other dots. So you can choose to teleport to any one of these, like this. And then you cannot go further. So clearly, it's a postspace. It is antisymmetric. And here, now, you try to describe the partial order around the corner of the square. Okay. So you are allowed to start here. Your point is duplicated. You can teleport. Once again, your point is duplicated. You can teleport. And once again, you see that you cannot go any further. So you really have something which is antisymmetric. So the diagram which is on the right just show you that this this partial order around the point is actually partitioned into 7 parts. So A times A star, and so on. And those arrows indicates, in some sense, the attachment of the part. And so you can see that this diagram is actually a DAG. So it has no directed loops, which in some sense shows that the order that the relation that we have described is indeed a partial order. It's not antisymmetric. Well, there is just one trick here that does not actually appear on the diagram. Sometimes there is two non-diomotopic ways to go from an element of the partition to the other. So it's hard to see, but for example, I will just leave my microphone for a while. If you take 2 points like that, which are identified, and you make them match here, you obtain indeed 2 directed paths with the same start and the same end, but they are not diagonal. Which means that the partial order, the pose space around the corner is not simple in the sense of the directed topology. Okay. Bop. C'est fini? Okay. Well, I'm over. Okay. So this very last slide is to show you that if you have to make the proof indeed, you have to compare every kind of partial order of your local order and check that they match. And here you have the 3 difficult cases to treat. And you can see that they are all solved by the same kind of common intersection. And then you have indeed the local order. Okay, but that's all. Thank you.
How general is this last construction? I mean, now you have shown it for one particular typical set. Is it true?
For any precubical set?
Yeah.
Yes. So I've written a proof, but I still proofed it myself because it's really awful. Basically, all the natural IDs you may have to prove this in a simple way cannot work, because if they were, they would also apply to cubical sets, and the result is wrong for cubical sets. And so at some point, you have to go into the details of the representation of the realization, and it's boring.
Okay, so exactly. Just a question. Is it easy to see that the geometric realization of a cubical set can have a vortex?
Of a cubical set? Oh yes, very easy. Oh, okay. Okay. Just consider one square. Identify the edges. You have a cylinder. You are in the world of cubical sets, so degeneracies are allowed. So you just say that the basis becomes 0-dimensional. You have a vortex. This is actually the it's the vortices in a cubical set realization are everywhere. Yeah, as soon as you produce a cone, it's done.
Okay, so let's continue.
Oh, merci à vous.